Precision is the closeness of various measurements, and accuracy is the agreement of a particular value to the true value of the result. In other words, precision is described as how close the values are when many measurements are made. For example, these dots show a high precision, but what about accuracy? Even though the dots are very precise, they are not accurate. Accuracy represents how close the value is to the real value. These dots show high accuracy but low precision. But this dartboard shows both a high accuracy as well as a high precision. Significant figures are the reliable digits in a number of measurement that are known with certainty. A measurement with more significant figures is more accurate than a number with less significant figures. All non-zero digits are significant. For example, in 2, 3, 4, 5 there are 4 significant figures. And in the number 0.579 there are 3 significant figures. Zeros that are followed by non-zero digits are not significant. For example, in 0.058 there are 2 significant figures. The zero that lies between 2 non-zero digits are significant. That is, there are 3 significant figures in 0.203. Zeros that follow the number after the decimal point are significant. There are 3 significant figures in 0.600. Zeros after decimal point and before non-zero numbers are not significant. Thus, there are 2 significant figures in 0.0032. Zeros that follow the numbers without decimal point are not significant. There is only 1 significant figure in 600. Now, can you tell why zeros in 600 are insignificant? Well, this is because 600 can be represented as scientific notation as 6 into 10 raised to 2. Hence, the significant number is 1. However, if this number is given in scientific notation as 6.00 into 10 raised to 2, the significant figures are 3. Counting numbers of objects have infinite significant figures. As these are exact numbers, they can be written in infinite number of zeros after placing a decimal. In scientific notation, all digits are significant. Addition and subtraction are carried out as a normal procedure, but the presentation of results is different. The digits after decimal point in the result should not be greater than either of the original numbers. On adding the numbers 5.6 and 8.24, we get the result of 13.84. So, the result should be reported as 13.8 because 5.6 has 1 digit after the decimal point. When the number 14.687 is subtracted from 58.64, the result obtained is 43.953, which should be reported as 43.95 because 58.64 has 2 digits after the decimal point. In multiplication and division, the result should not have greater significant figures than the original numbers. When the numbers 4.58 and 2.1 are multiplied, the result obtained is 9.618. This result should be reported as 9.6 because 2.1 has only 2 significant figures. When the number 8.32 is divided by 1.2, 6.9333333 is obtained as the answer, which can be reported as 6.9 because 1.2 has only 2 significant figures. Rules to limit the number of significant figures in mathematical operation. If the rightmost number that is to be removed is greater than 5, then the preceding number is increased by 1. That is, 5.238 is reported as 5.24. If the rightmost digit that is to be removed is less than 5, then the preceding number is not changed. For example, 8.312 is reported as 8.31. If the dropping number is 5 and the preceding number is odd, then it is increased by 1. But if the preceding number is even, then it is not changed. For example, 5.375 is reported as 5.38 and 5.445 is reported as 5.44. Any calculation that involves the use of dimensions of the different physical quantities involved is called dimensional analysis. It is used to convert a physical quantity given in one type of unit into some other unit. It is also used to obtain the correct units when problems are being solved. For example, let us convert 125 pounds into kilograms. The unit of weight in pounds gets cancelled out from the numerator and the denominator, and we get the required answer.
Chemistry, physics, biology, etc.
Chemistry is the branch of science which deals with the study of composition, structure, and properties of matter, and changes which matter undergoes under different conditions.
Chemistry has a reputation for being a complicated and boring science, but for the most part, that reputation is undeserved. Fireworks and explosions are based on chemistry, so it's definitely not a boring science. Even your body is made of chemicals. Chemical reactions occur when you breathe, eat, or just sit there reading. All matter is made of chemicals, so the importance of chemistry is that it's the study of everything. The gas and tires in cars we drive, the makeup we put on our faces, the soaps and cleaners used every day, burning wood or other fossil fuels. Chemistry is all around you each and every day. The associations are practically limitless. So, as you go about your daily activities, remember to thank chemistry. Chemistry is at the heart of environmental issues. What makes one chemical a nutrient and another chemical a pollutant? How can you clean up the environment? What processes can produce the things you need without harming the environment?
Chemistry is important in agriculture. It is very important in the production of fertilizers, pesticides, preservatives, etc. Also, many of the life-saving drugs and other medicines are being prepared by chemists.
Life-saving drugs such as cisplatin and Taxol are effective in cancer therapy.
With better understanding of chemical principles, we can now design and synthesize new materials having specific properties.
We're all chemists. We use chemicals every day and perform chemical reactions without thinking much about them. Chemistry is important because everything you do is chemistry. Nature of matter. Everything which has mass and occupies space is called matter. Everything around us, the air we breathe, the water that we drink, the books we read, the car that we drive, everything is made of matter. Atoms are the basic building blocks of matter that make up everyday objects. We know that matter can be classified into three physical states: solid, liquid, and gas. Let us take the example of water to learn more about these three states of matter. Water in solid state is called as ice. As you can see, the constituent particles are held close to each other in an orderly manner. Because of this, solids have definite shape and volume. When water is in the liquid state, the particles are still close to each other, but they can move around. Because of this, liquids have definite volume, but no definite shape, and so they take the shape of the container in which they are kept. When water is in the vapor form, the particles are far apart as compared to those present in solid or liquid states, and their movement is also quite free and fast. Because of this, the gases have no definite shape or volume, and they completely occupy all space that is available to them. As we saw, all these states of matter were interconvertible by changing the conditions of temperature and pressure. Heating can change a substance from solid to liquid to gas, while the cooling process will achieve the reverse effect. We can broadly classify matter as mixtures or pure substances. When any substance is made up of only one kind of component, it is called a pure substance. For example, the graphite in the pencil that we use to write is made up of only carbon atoms. Hence, it is a pure substance. Such substances which have only one type of atoms are called as elements. But different elements have different atoms. For example, an atom of sodium is different from an atom of oxygen. The water that we drink is made up of only water molecules, so it is also a pure substance. In all water molecules, 2 atoms of hydrogen and 1 atom of oxygen is present. Thus, they are always in a fixed ratio. All elements and compounds are pure substances. Also, the properties of the compound are usually different from its constituent elements. Like as we saw, water is a liquid, but its constituent elements, hydrogen and oxygen, as we know, are gases. Also, hydrogen burns easily, while oxygen supports combustion on the other hand. Water is used as a fire extinguisher. Some substances are made up of more than one substance, which can be in any ratio. They are called as mixtures. For example, air has molecules of nitrogen, oxygen, water, carbon dioxide, etc. But these components are not easily distinguishable. Hence, it is a homogeneous mixture. While in some mixtures, it is easy to separate out the components. For example, the stones that can be easily picked out from the mixture of grains and pulses. Also, when you pour oil in water, they form separate layers. Both of them are examples of heterogeneous mixtures, as the composition of components is not uniform, and the different components can be easily observed.
There are only 2 kinds of pure substances, elements and compounds. When any substance is made up of only one kind of component, it is called a pure substance. Thus, elements and compounds are considered to be pure substances. It has the same color, taste, texture and composition. Also, it is made out of a same particle. Elements are the simplest form of matter and cannot be broken down using chemical methods into 2 or more pure substances. For example, iron is a pure substance. You can take a piece of iron and break it down into smaller and smaller pieces, but each of these smaller pieces has the same properties as the starting material. Hence, it is always the same substance. Sodium, copper, oxygen, hydrogen, carbon, nitrogen, etc. are some of the examples of elements which contain atoms of only one type. Compounds, on the other hand, can be broken down into 2 or more pure substances. For example, H2O or water can be broken down into H2, hydrogen gas, and O2, oxygen gas. The examples of some compounds are water, ammonia, carbon dioxide, etc. Observe that a water molecule comprises 2 hydrogen atoms and 1 oxygen atom, and a molecule of carbon dioxide contains 2 oxygen atoms and 1 carbon atom. Thus, the atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound.
And molar masses. People need nails, lot of nails. Counting lots of nails is a very tedious task because they are small and pointy. Hardware store owners solved the problem long ago with a method that can be applied to almost everything, including chemistry. Shopkeepers decided on an easier method than counting each individual nail. They simply sold nails by weight. Molecules are so tiny that instead of counting individual particles, we may want to count a chemist's dozen or mole of molecules instead. Atoms and molecules are counted indirectly by weighing. The 12 gram of carbon contains a certain number of atoms of carbon. This number is estimated to be 6.023 into 10 raised to 23 and is called Avogadro's number. Thus 12 grams of the carbon 12 is 1 mole of carbon. Avogadro's number is found to be 602.000000000000000000000. That is 6.02 into 10 raised to 23. It is usually designated by Na. The mole, abbreviated MOL, is the SI measure of quantity of a chemical entity, which can be an atom, molecule, formula unit, electron, or photon. 1 mole of anything is just Avogadro's number of that something. Or if you think like a lawyer, you might prefer the official SI definition. 1 mole is the amount of a substance that contains as many particles or entities as there are atoms in exactly 12 grams or 0.012 kgs of the 12C isotope. Molar mass. We've looked at the mole in detail. Now it is easier to understand the term molar mass. It is the mass of 1 mole of a substance in grams. It is numerically equal to atomic or formula or molecular mass in U. For example, molar mass of water is equal to 18.02 grams per mole. Molar mass of sodium chloride, NaCl, is equal to 58.5 grams per mole. Molar mass of benzene is equal to 342.297 grams per mole. So, 3 possible ways of specifying the amount of a chemical are possible: by mass, by weight, by mole, by molecular count. These are obviously interconvertible
measurement. Each substance has characteristic properties. These properties can be classified into 2 categories: physical properties and chemical properties. Physical properties can be observed or measured without changing the composition of matter. Physical properties are used to observe and describe matter. Physical properties include color, odor, appearance, temperature, etc. Melting point and boiling point are physical properties of matter. For example, melting point and boiling point of water. Solubility is also a physical property. The measurement or observation of chemical properties requires a chemical change to occur. Charcoal or burning of matches shows their chemical properties. The International System of Units, SI.
The measurement of any physical quantity consists of 2 parts, a number and a unit. For a particular quantity, many different units may be used.
For example, the speed v of a car may be expressed in the form v equals 25 meter per second equals 90 kilometers per hour, where meter per second and kilometer per hour are alternative units for expressing the same value of the quantity speed. But the existence of alternative units can create problems. As an analogy, if you are traveling in a foreign country, the local shopkeeper might not accept rupees as they use a different currency unit. However, in many countries of Europe, they use a single centralized currency, the euro. You can use the same currency unit, the euro, wherever you go in the countries that have accepted euro as the currency. Similarly, a scientist in one country might need to read a research paper by a scientist in another country. It might be difficult for him to understand the paper if some very different units have been used for scientific measurements in that paper. To solve these problems, a system of units should be universally agreed upon to avoid confusion between scientists throughout the world. However, the units should be chosen so that they are readily available to all, are constant throughout time and space.
In 1960, an international agreement was reached specifying a particular choice of metric units for use in scientific measurement. These preferred units are called SI units, after the French Le Système International d'Unité.
The SI system has 7 base units from which all other units are derived. These 7 base units are for mass, length, time, temperature, amount of substance, electric current, and luminous intensity. The table here lists these base units and their symbols. In this chapter, we will consider the base units for length, mass, and temperature. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities. Prefixes are used to indicate decimal fractions or multiples of various units. This table presents the prefixes commonly encountered in chemistry. Let us now consider the quantities which are used widely in chemistry. First is length. Unit of length is meter, and its definition is given as follows. The meter is the length of the path travelled by light in vacuum during a time interval of 1 by 299,792,458 of a second. Second is mass. Unit of mass is kilogram, and its definition is given as follows. Mass is a measurement of the amount of material in an object. The kilogram is the unit of mass. It is equal to the mass of the international prototype of the kilogram. Third quantity is time. Unit of time is second. The second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the Ca-133 atom. Fourth quantity is electric current. Unit of electric current is ampere. The ampere is that constant current which, if maintained in two straight parallel conductors of infinite length, of negligible circular cross-section, and placed 1 meter apart in vacuum, would produce between these conductors a force equal to 2 × 10⁻⁻⁷ Newton per meter of length. Fifth quantity is thermodynamic temperature. Unit of thermodynamic temperature, Kelvin. The Kelvin, unit of thermodynamic temperature, is the fraction 1 by 273.16 of the thermodynamic temperature of the triple point of water. Sixth quantity is amount of substance. Unit of amount of substance is mole. The mole is the amount of substance of a system, which contains as many elementary entities as there are atoms in 0.012 kilogram of carbon-12. Its symbol is mole. When the mole is used, the elementary entities must be specified and may be atoms, molecules, ions, electrons, other particles, or specified groups of such particles. Seventh quantity is luminous intensity. Unit of luminous intensity is candela. The candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 by 1012 Hz, and that has a radiant intensity in that direction of 1 by 683 watt per steradian. Now we will understand some of these units in detail. Mass and weight. Do you know the difference between mass and weight? Mass is a measure of the amount of matter present in a substance. Look at these two cubes. Which of them has more matter, the bigger one or the smaller one? Let us find out. As we already know, scientists have decided the mass of a platinum iridium alloy kept in Sèvres, France, to be a standard 1 kilogram. This is used as a reference to measure all other masses. Using a beam balance, we see that 5 prototypes are used to balance the bigger block, hence its mass is 5 kilograms, while 10 prototypes are used to balance the smaller block, so its mass is 10 kilograms. So in this case, it is actually the smaller block that has more mass. Now, weight is the amount of gravitational force pulling a body. If the mass of a body on Earth is 10 kilograms, then its weight is nearly 100 Newton. Let us take the same body to the Moon. The Moon is smaller than the Earth, and its gravity is only 1/6 that of the Earth. So on the Moon, its weight becomes only 16 newtons. During this journey, the amount of matter in the cube has not changed, but its weight changed. In laboratories, we use an analytical balance as shown. The SI unit is kilogram, but grams is used in laboratories due to the smaller amounts of chemicals used in chemical reactions. Now, let us study volume. Volume is the amount of space occupied by an object. The SI unit of volume is cubic meter. However, this quantity is too large to be practical for the laboratory, so smaller volumes are used. Hence, volume is often denoted in centimeter cube or cubic decimeter units. A common unit, liter, L, which is not an SI unit, is used for measurement of volume of liquids. 1 liter equals 1000 ml, 1000 centimeter cube equals 1 decimeter cube. In the laboratory, Volume of liquids or solutions can be measured by graduated cylinder, burette, pipette, etc. Now, let us define density. Density of a substance is its amount of mass per unit volume. So, SI units of density can be obtained as follows. SI unit of density is equal to SI unit of mass by SI unit of volume, which has a unit of kilogram per meter cube. This unit is quite large, and a chemist often expresses density in grams per centimeter cube, where mass is expressed in grams and volume is expressed in centimeters cubed. Now, let us study temperature. It is summer. You are feeling hot. You exclaim, "Oh, how hot it is!" But how will you tell someone exactly how hot it is? You want to bake a cake. You know that you have to heat the batter. But how will you know how much to heat? To measure heat, to give a value to it, we use temperature scales. There are three common scales to measure temperature: degree Celsius, degree Fahrenheit, and Kelvin. Here, K is the SI unit. The thermometers based on these scales are shown here. We sense temperature as a measure of the hotness or coldness of an object. We can understand the temperature scale by comparing with various references. The Celsius scale is based on the assignment of 0 degrees Celsius to the freezing point of water and 100 degrees Celsius to its boiling point at sea level. The Kelvin scale is the SI temperature scale, and the SI unit of temperature is the Kelvin. Historically, the Kelvin scale is based on the properties of gases. 0 on this scale is the lowest attainable temperature, minus 273.15 degrees Celsius, a temperature referred to as absolute zero. The Kelvin and Celsius scales are related as follows. Kelvin is equal to degree Celsius plus 273.15. The Fahrenheit and Celsius scales are related as follows. Degree Celsius is equal to 5 by 9 into degree Fahrenheit minus 32, or degree.
Scientific notation. Chemistry deals with the study of atoms and molecules. The chemist who studies these atoms and molecules has to juggle between very large and very small numbers, because the atoms and molecules we are referring to are found in extremely large numbers and have extremely small masses. This chemist is studying hydrogen. The chemist is confronted by as many as 602 sextillion, 200 quintillion molecules in just 2 grams of hydrogen gas. When he deals with one atom of hydrogen, he is dealing with a mass as less as 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 on these numbers. It is difficult to handle such numbers, and there is a very high chance of making errors in the calculations involving them. To solve this problem, the numbers are written in a form called the scientific notation or exponential notation. In this form of representation, the numbers are expressed as follows: n multiplied by 10 raised to n. Here, n can vary between 1 to 10. N is the exponent, and it may have positive or negative values. Let us see how this is done. Let's take a number, say 232.508. We need to bring this number to the scientific notation n multiplied by 10 raised to n. We take 232.508, and as n has to be between 1 to 10, we move the decimal 2 places to the left, and it becomes 2.32508. As we move the decimal 2 places, the exponent of 10 becomes 2. As we move the decimal to the left, the value of the exponent is positive. Now, let's take another number, say 0.00016. We move the decimal 4 places to the right to bring the number between 1 to 10. The exponent of 10 thus becomes 4, and because we moved the decimal to the right, the exponent has a negative sign. It is convenient to perform operations like addition, subtraction, multiplication, and division on numbers in the scientific notation or exponential form, but we need to follow some rules. Let's first see the rules for multiplication and division, as these two operations follow the same set of rules. When we multiply two numbers in exponential form, the n is multiplied and the exponents of 10 are added. For instance, if two numbers 4.4 into 10 raised to 2 and 2.3 into 10 raised to 5 are multiplied, the product would be 10.12 into 10 raised to 7. If 3.32 into 10 raised to minus 4 is to be multiplied by 1.26 into 10 raised to minus 3, the product would be 4.18 into 10 raised to minus 7. If two numbers in exponential form are to be divided, the n is divided and the exponents of 10 are subtracted. If we are to divide 14.22 into 10 raised to 7 by 2.44 into 10 raised to 3, the quotient will be 5.83 into 10 raised to 4. If we divide 9.34 into 10 raised to minus 3 by 5.67 into 10 raised to 4, we get 1.65 into 10 raised to minus 7. Now let's look at the rules for addition and subtraction of numbers in exponential notation. For both addition and subtraction, the decimal in the coefficient n are adjusted, and the exponents of 10 are made to be the same in the numbers to be added or subtracted. The coefficients are then added or subtracted as the case may be. Let's take an example. If 2.3 into 10 raised to 3 and 3.4 into 10 raised to 4 are to be added, the exponents are first made the same by moving the decimal point. Then the coefficients are added, and thus the sum obtained is 3.63 into 10 raised to 4. If 2.7 into 10 raised to minus 3 is to be subtracted from 7.6 into 10 raised to minus 2, the coefficients are subtracted after making the exponents of 10 the same for the two numbers. The answer obtained will be 7.33 into 10 raised to minus 2. Significant figures. Whenever one performs an experiment and measures a value, the measurement is bound to have some amount of uncertainty. But ideally, we would like the measurements taken to be precise and accurate. Let us try and understand what the terms precision and accuracy actually mean. Precision is the closeness of the measurements taken for the same quantity. Accuracy, on the other hand, refers to the agreement of the values measured to the true value. Let us assume that three individuals are performing an experiment. Each one arrives at a different set of values. The true value for the measurement is 20 milliliters. In the first case, the individual has taken two measurements, 19.5 milliliters and 19.3 milliliters. As these values are close to each other, they can be said to be precise. Note that these values are not close to the true value, 20 milliliters, and hence cannot be termed as accurate. In the second case, the individual records two measurements, 19.4 milliliters and 20.5 milliliters. These readings are neither precise nor accurate, as they are neither close to each other nor to the true value. In the third case, the individual arrives at two measurements, 20.1 milliliters and 19.9 milliliters respectively. These measurements are both precise and accurate. In order to express any uncertainty in a measured or calculated value, we make use of significant figures, which are the digits in a properly recorded measurement. They are the meaningful digits in a measurement or calculated quantity. The greater the number of significant figures, smaller is the uncertainty and greater is the precision. Significant figures are therefore meaningful digits which are known with certainty. The uncertainty is indicated by writing the certain digits and then the last uncertain digit. Thus, if we write a result as 14.6 milliliters, we say that 14 is the value known with certainty and 6 is uncertain. There is always an uncertainty of plus or minus 1 in the last digit. Unless mentioned otherwise, an uncertainty of plus or minus 1 in the last digit is always assumed.
The following rules are used to determine the number of significant digits in a recorded measurement. Digits other than 0 are always significant. 973 has 3 significant digits. 7.3 has 3 significant digits. 9.7 has 2 significant digits.
Zeros at the end or right of a number are significant provided they are after the decimal point.
9.7300 has 5 significant digits. Zeros between two other significant digits are always significant. 9.073 has 4 significant digits. Zeros used solely for spacing the decimal point are not significant. 3000 has 1 significant digit. 0.00973 has 3 significant digits. The zeros are placeholders only. Once we have recorded measurements to the correct number of significant digits and expressed them in scientific notation, if appropriate, we are ready to use these measurements in calculations. To determine the number of digits that should appear in the answer to a calculation, we will use two rules. In addition and subtraction, the answer may contain only as many decimal places as the least accurate value used in finding the answer. For example, if a whole number like 655 is added to 25.3, the answer must be given to the nearest whole number. In adding a column of figures such as 606 plus 35.3 plus 5.31 plus 112.16, the answer should be rounded off to the nearest whole number. The answer to the problem above is 759. In multiplication and division, the answer may contain only as many significant digits as the least accurate value used to arrive at the answer. For example, in the following problem, 1.143 into 4.126000 equals, since 1.143 has 4 significant figures, the result should not have been more than 4 significant figures. The answer, 4.176018, should be represented as 4.176. If you are using a calculator to obtain your numerical answer, you must be very careful. The calculator may give you an answer with 8 or 10 digits.
For example, in the problem 57.4000 by 54.30, the answer may appear as 1.388581952. The answer must be rounded to the proper number of significant digits.
We have already studied the 3 gas laws which explain the interrelationship between pressure, volume, and temperature. Avogadro found out that the quantity or the number of molecules of the gas is directly related to its volume, but it was necessary that the pressure as well as the temperature were maintained constant. Just for the purpose of understanding, let's take up a hypothetical activity. We have 2 identical balloons. These 2 balloons are to be filled up with 2 different gases, gas A and gas B. We fill the first balloon with, let's say, 1,000,000 molecules of gas A. The balloon gets inflated to an extent. Thereafter, we inflate the second balloon with, again, 1,000,000 molecules of gas B. This balloon also gets inflated to the same size as the first one. This means that 2 gases, if taken in the same quantity, will have the same volume. Of course, both the balloons were present in the same room and hence were at the same temperature. Moreover, as both the balloons were identical, the gases were at same pressure. Avogadro had come to the following conclusion. Equal volumes of gases at the same temperature and pressure should contain equal number of molecules.
Law of definite proportion.
The law of definite proportions, first defined by Joseph Louis Proust, states that a given compound always contains exactly the same proportion of elements by weight. For example, no matter what amount of water, H2O, you have, or whatever the source may be, there will always be a ratio of 1/9 hydrogen to 8/9 oxygen, whether the sample size is a drop of water or a lake.
In other words, we know that water is always composed of 2 hydrogen and 1 oxygen atom, typically about 88.8% oxygen to about 11.2% hydrogen by mass. It is sometimes also referred to as law of definite composition, but 2 elements can combine in different ratios in different compounds, like hydrogen and oxygen combine in the ratio 2:1 to form water, which is different from hydrogen peroxide in which they combine in the ratio 1:1. Law of multiple proportions. This law, composed by John Dalton, based on the law of definite proportions, was the basis of chemical formulas for compounds. For example, the oxygen compared between CO and CO2 has a simple 1:2 ratio. 1 oxygen in the first compound, 2 oxygen in the second compound. 100 grams of carbon will react with either 133 grams of oxygen to produce carbon monoxide, or with 266 grams of oxygen to produce carbon dioxide. In water, hydrogen and oxygen combine in the ratio 2:1, and in hydrogen peroxide, they combine in the ratio 1:1. So, it is clear that the ratio of mass of oxygen, which combines with a fixed mass of hydrogen, bears a simple ratio of 1:2. This leads us to the law of multiple proportion, which states, whenever two elements form more than one compound, the different masses of one element that combine with the same mass of the other element are in the ratio of small whole numbers. Gay-Lussac's law of gaseous volume. This law was given by Gay-Lussac in 1808.
The law of combining volumes states that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at the same temperature and pressure.
The ratio between the volumes of the reactant gases and the products can be expressed in simple whole numbers. For example, nitrogen and hydrogen react to form ammonia gas. In this example, 1 volume of nitrogen gas reacts with 3 volumes of hydrogen gas to produce 2 volumes of ammonia gas. Similarly, 100 ml of hydrogen combines with 50 ml of oxygen to give 100 ml of water vapor.
Thus, the volumes of hydrogen and oxygen combine together in a simple ratio of 2:1. This volume relationship is the law of definite proportions by volume.
Avogadro Law. In 1811, Avogadro proposed that equal volumes of gases at the same temperature and pressure should contain equal number of molecules. We see two ideal gases, helium and neon, taken in equal proportion. Pressure and temperature of gases are equal and constant. The number of moles or molecules of both the gases is same. As we increase the number of molecules, the volume of gas in the container increases. Consider again the reaction of hydrogen and oxygen producing water. We can observe that 2 volumes of hydrogen combine with 1 volume of oxygen to give 2 volumes of water without leaving any unreacted oxygen. Note that here each box contains equal number of molecules. This also applies to the polyatomic molecules. We have learnt about mole, atomic, molecular and formula weights. We can move on to calculations where these concepts can actually be used. Here is Mr. Balance. Here, lithium and nitrogen combine to give lithium nitride. We can see that on the product side, there is only 1 nitrogen atom, but on the reactant side, there are 2 nitrogen atoms. So we balance it by multiplying the product side by 2. Now, let us check whether lithium is balanced or not. Here we can see that on the product side, there are 6 lithium atoms, but on the reactant side, there is only 1 lithium atom. We multiply lithium on the reactant side by 6 to balance the number of lithium atoms on both the sides. Hence, the number of nitrogen atoms and lithium atoms is equal on both the sides. This gives us a balanced equation. Stoichiometry thus deals with the calculation of masses, sometimes volumes also, of the reactants and the products involved in a chemical reaction.
Calculate the amount of water G produced by the combustion of 32 grams of methane. The balanced equation for combustion of methane is CH4 gas plus 2 O2 gas gives CO2 gas plus 2 H2O gas. 32 grams of CH4 corresponds to 2 moles. From the above equation, 2 moles of CH4 gas gives 4 moles of H2O gas. 4 moles of water H2O equals 4 into 2 plus 16 equals 4 into 18 equals 72 grams. Now, 1 mole H2O equals 18 grams H2O. This implies that 18 grams H2O by 1 mole H2O equals 1. Hence, 4 mole H2O into 18 grams H2O by 1 mole H2O equals 4 into 18 grams H2O, which is equal to 72 grams of water.
Limiting reagent.
We have a beaker to which we add a volume of HCl containing 0.10 mole HCl and a volume of NaOH solution containing 0.20 mole of NaOH.
As we can see, these two react to form NaCl and H2O. HCl plus NaOH gives NaCl plus H2O. However, since the quantity of HCl is lesser than that of NaOH, after some time there are molecules of NaOH left which cannot react with HCl as the quantity of HCl is exhausted. This limits the amount of NaCl that can be produced. Hence, HCl is called the limiting reagent, as it limits the amount of product that is formed as it is present in lesser amounts. Expressing concentration of solutions. Let us see how we can express the composition of a solution in terms of its concentration in different ways. We can describe the composition of a solution through its concentration, either qualitatively or quantitatively. For example, qualitatively, we can say that the solution lighter in color is dilute. That is, it has a low amount of solute, and the darker solution is concentrated. That is, it has a high amount of solute. But such a classification can lead to a lot of confusion. Suppose a medicine is to be made, then we need the exact proportions of the constituents. Too less or too much of the solute could cause complications. In such cases, a proper quantitative description becomes important. The concentration of a solution can be expressed in several ways. Let us see them one by one. Mole fraction, chi. Let us understand the concept of mole fraction with the example of a fruit salad. This fruit salad has 10 pieces of apple, 15 banana pieces, 10 pineapple pieces, and 25 grapes. So now there are a total of 10 plus 15 plus 10 plus 25 equals 60 pieces of fruit in our fruit salad. Out of these 60 pieces of fruit, the fraction of banana pieces that we have is 15 by 60 equals 25%. Now, just like a solution has different components, the different fruits are the components of the fruit salad. Let us assume a piece of fruit to be equivalent to a mole of a component of the solution. So now the fraction of the banana pieces present in the fruit salad can be said to be as the mole fraction of the banana in the fruit salad. For a fruit salad containing I number of fruits, the fraction of a specific fruit will be chi I equals ni upon n1 plus n2 and so on till ni, which is further equal to ni upon summation ni. This will also be the mole fraction for a solution containing I number of components. Now in the fruit salad, the mole fraction of the banana pieces was 15 by 60 or 25%. The mole fraction of both apple pieces and pineapple pieces is 10 by 60 or 16.6%. while the mole fraction of grapes is 25 by 60 or 41.66%. When we add all of them, we get 15 by 60 plus 10 by 60 plus 10 by 60 plus 25 by 60 equals 1. Similarly, in a given solution, the sum of all the mole fractions will be unity. Chi 1 plus chi 2 and so on up to chi I equals 1.
We can also consider the fraction concept for a molecule. This is called mole fraction. It is the ratio of number of moles of a particular component to the total number of moles of the solution. If a substance A dissolves in substance B and their number of moles are Na and Nb respectively, then the mole fractions of A and B are given as mole fraction of A is equal to number of moles of A by number of moles of solution. This is equal to Na by Na plus Nb. Also, mole fraction of B is equal to number of moles of B by number of moles of solution. This is equal to Nb by Na plus Nb.
Molarity. We know that the molar mass of NaOH is 40 grams. Let us add 0.25 moles or 10 grams of NaOH to water. We will add water till the volume of solution is 1 liter. Thus, we have made a 0.25 molar solution of NaOH. So now, molarity can be defined as Molarity equals moles of solute by volume of solution in liter. The unit of molarity will be mole per liter or m. So, we had made a 0.25 mole per liter or 0.25 m NaOH solution.
If 1 mole is present in 1 liter or 1000 milliliters, then 0.25 mole is present in 1000 mole by 1 mole into 0.25 mole equals 250 ml. So 250 ml of 1 mole NaOH are taken and enough water is added to dilute it to make it 1 liter. For such calculations, a general formula M1 into V1 equals M2 into V2 is used. Here, M and V are molarity and volume respectively. M1 V1 equals M2 V2. Here, M1 equals 0.25, V1 equals 1000 milliliter, and M2 equals 1.0. 0.25 m into 1000 ml equals 1.0 m V2. Therefore, V2 equals 0.25 m into 1000 ml by 1.0 m equals 250 milliliter.
Molality, M. We know that the molar mass of KCl is 74.5 grams. Let us add this amount of KCl, that is, 1 mole of KCl to 1 kilogram of water. Thus, we have created a 1 molal solution of KCl. Molality can be defined as molality M equals moles of solute by mass of solvent in kilograms. So the units of molality will be mole per kilogram.
1.1. Calculate the molecular mass of sucrose, C12H22O11. Solution: the molecular mass of sucrose, C12H22O11 is 12 into atomic mass of C plus 22 into atomic mass of H plus 11 into atomic mass of O equals 12 into 12.011 U plus 22 into 1.008 U plus 11 into 16.00 U equals 144.132 plus 22.176 plus 176 equals 342.308 U. Example 1.2. The mass percentage of elements in a compound is H equals 9.15%, C equals 54.53%, O equals 36.32%. The molecular mass of the compound is 132.16 U. Find the empirical formula and the molecular formula for the compound. Solution. Step 1. Conversion of mass percent to grams. From the mass percentage of elements, we can say that 100 grams of the compound contains 9.5 grams of hydrogen, 54.53 grams of carbon, and 36.32 grams of oxygen. Step 2. Convert into number of moles of each element. We divide the above obtained masses by their respective atomic masses to get the number of moles of each element. Number of moles of hydrogen equals 9.5 by 1.008 equals 9.42. Number of moles of carbon equals 54.53 by 12.01 equals 4.54. Number of moles of oxygen equals 36.32 by 16 equals 2.27. Step 3. Divide the mole value obtained above by the smallest number. In our case, the lowest mole value is 2.27. We divide all the three mole values to get a ratio. For O, 2.27 by 2.27 equals 1. For H, 9.15 by 2.27 equals 4. For C, 4.54 by 2.27 equals 2. Thus, the ratio of the elements is 1:4:2 for O is to H is to C. In other words, for C is to H is to O, the ratio will be 2:4:1. Step 4. Write empirical formula by mentioning the numbers after writing the symbols of respective elements. From the ratio, we have the empirical formula to be C2H4O. Step 5. Writing the molecular formula. The empirical formula mass for C2H4O is 2 into 12.01 plus 4 into 1.008 plus 1 into 16 equals 24.02 plus 4.032 plus 16 equals 44.052 grams. We divide molar mass by empirical formula mass to get N equals 132.16 by 44.052 equals 3. We now multiply the empirical formula by N to get the molecular formula as C2 into 3 H4 into 3 O1 into 3 equals C6 H12 O3. Example 1.3. Find the amount of water produced by combustion of 32 grams of methane gas. Solution. Molecular weight of CH4 equals 1 into 12 plus 4 into 1 equals 12 plus 4 equals 16 grams. We write a balanced chemical equation of the reaction. CH4 gas plus 2O2 gas gives CO2 gas plus 2H2O gas. From the equation we can say that 1 mole of CH4 gas gives 2 moles of H2O gas. The molecular weight of 2 moles of H2O equals 2 into atomic mass of H plus 1 into atomic mass of O equals 2 into 1 plus 1 into 16 equals 2 into 18 equals 36 grams. Thus, 2 moles of H2O gas would weigh 36 grams. We can now say that 16 grams of CH4 gas produces 36 grams of H2O gas. Therefore, 32 grams of CH4 gas would produce 36 into 32 by 16 equals 72 grams. Hence, combustion of 32 grams of methane produces 72 grams of water, gas. Example 1.4. Calculate the number of moles of methane gas required to produce 88 grams of CO2 gas on combustion. Solution. Molecular mass of CH4 equals 1 into 12 plus 4 into 1 equals 12 plus 4 equals 16 grams. Molecular mass of CO2 equals 1 into 12 plus 2 into 16 equals 12 plus 32 equals 44 grams. We write a balanced chemical equation for the reaction. CH4 gas plus 2O2 gas gives CO2 gas plus 2H2O gas. From the equation we can say that 1 mole of CO2 gas is obtained by burning 1 mole of CH4 gas. Thus, 44 grams of CO2 gas is obtained by burning 16 grams of CH4 gas. Thus, 88 grams of CO2 gas would be obtained by burning equals 88 into 16 by 44 equals 32 grams of CH4 gas. 16 grams of CH4 gas constitutes 1 mole of CH4 gas. Thus, 32 grams of CH4 gas would constitute 32 into 1 by 16 equals 2 moles of CH4 gas. Therefore, 2 moles of CH4 is required to produce 88 grams of CO2. Example 1.5. 60 kilograms of N2 gas and 10 kilograms of H2 gas combine to produce NH3 gas. Find the amount of NH3 gas formed. Also, identify the limiting agent in this process. Solution. Molecular weight of NH3 gas equals 1 into atomic mass of N plus 3 into atomic mass of H equals 1 into 14 plus 3 into 1 equals 17 grams. Let us write the balanced chemical equation for this reaction. N2 gas plus 3H2 gas gives 2 NH3 gas. Moles of N2 equals 60 kilograms N2 into 1000 grams N2 by 1 kilogram N2 into 1 mole. N2 by 28 grams N2 equals 21.43 into 10 raised to 2 moles. Moles of H2 equals 10 kilogram H2 into 1000 grams H2 by 1 kilogram H2 into 1 mole H2 by 2.016 grams H2 equals 4.96 into 10 raised to 3 mole. As per the above chemical equation, we can see that 1 mole of N2 requires 3 moles of H2 for the reaction. Hence, 21.43 into 10 raised to 2 moles of N2 would require 21.43 into 10 raised to 2 moles N2 into 3 moles H2 by 1 mole N2 equals 64.29 into 10 raised to 3 moles H2. But we have only 4.96 into 10 raised to 3 moles H2. Hence, dihydrogen becomes the limiting reagent in this case. Hence, the amount of NH3 formed shall depend on the amount of dihydrogen present, meaning it would be formed only from 4.96 into 10 raised to 3 moles. Since 3 moles H2 gives 2 moles NH3, 4.96 into 10 raised to 3 moles H2 gives 4.96 into 10 raised to 3 into 2 by 3 equals 3.3 into 10 raised to 3 moles NH3. Conversion to grams is done as follows. 1 mole NH3 equals 17 grams of NH3. Hence, 3.3 into 10 raised to 3 moles NH3 equals 3.3 into 10 raised to 3 into 17 grams NH3 by 1 mole NH3 equals 56.1 kilogram NH3. Example 1.6. 2 grams of substance A is added to 36 grams of water. Find the mass percentage of the solute. Solution. Total mass of the solution equals 36 plus 2 equals 38 grams. Mass percentage of the solute equals mass of solute by total mass of solution into 100 equals 2 by 38 into 100 equals 5.26%. Example 1.7. Find the molarity of NaOH in a solution when 4 grams of NaOH is dissolved in water to form 250 milliliters of the solution. Solution. We know that molarity M equals number of moles of solute by volume of solution in liters. To find the number of moles, we need to know the molecular mass of NaOH. Molecular mass of NaOH equals 1 into atomic mass of Na plus 1 into atomic mass of O plus 1 into atomic mass of H equals 1 into 23 plus 1 into 16 plus 1 into 1 equals 40 grams. Thus, number of moles of NaOH dissolved equals 4 grams by 40 grams equals 0.1 mole. Therefore, M equals 0.1 mole by 0.25 liters equals 0.4 mole per liter or 0.4 m. Thus, the molarity of NaOH in the solution is 0.4 m. Example 1.8. The density of a 0.667 m solution of glucose is 1.2 grams per milliliter. Calculate the molality of the solution. Solution. M equals 0.667 moles per liter. Mass of glucose in 1 liter of solution equals 0.667 into 180 equals 120 grams. Mass of 1 liter solution equals 1000 into 1.2 equals 1200 grams. Mass of solvent, water, equals 1200 minus 120 equals 1080 grams equals 1.08 kilograms. We know that molality of a solution is given as molality equals number of molecules of solute by mass of the solvent in kilograms equals 0.667 by 1.08 equals 0.61
in 2 mangoes. Therefore, total is equal to 2 plus 1 plus 3 plus 2, which is equal to 8. What is the percentage of apples in the fruit basket? It is 25%.
Similarly, even in molecules, the percentage composition of atoms in a molecule can be calculated. Here, glucose has the formula of C6H12O6.
Suppose an unknown or new compound is given to you. The first question you would ask is, what is its formula? As we can see here,
the percentage of carbon in glucose can be calculated by taking mass fraction of carbon in the total mass of glucose. So the percentage of carbon in glucose is equal to atomic mass of 6 carbon atoms divided by molecular mass of glucose molecule into 100. Putting the values, we can calculate percentage composition of carbon in glucose as 40%.
This gives us the answer as 40%. Similarly, percentage of hydrogen in glucose is equal to atomic weight of 12 hydrogen atoms by the molecular weight of glucose. This gives us percentage of hydrogen in glucose as 6.66%. And percentage of oxygen in glucose is equal to atomic weight of 6 oxygen atoms by the molecular weight of glucose. This gives us the percentage of oxygen in glucose as 53.33%. Empirical formula for molecular formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound. As given in the table, molecular formula and empirical formula of various hydrocarbons are given. Acetylene has an empirical formula of C2H2, but if we take only ratio of carbon and hydrogen, it can be written in a simple form like CH, which is its empirical formula. Similarly, benzene also has the empirical formula as CH, while ethylene and cyclohexane.
Let us take an example to understand the steps involved in finding empirical formula for molecular formula. A compound contains 4.07% hydrogen, 24.27% carbon, and 71.65% chlorine. Its molar mass is 98.96 grams. Find its empirical and molecular formulas. Step 1. Conversion of mass percent to grams. As we are having mass percent, it is convenient to take 100 grams of the compound as the starting material. Thus, in the 100 gram sample of the above compound, 4.07 grams hydrogen is present, 24.27 grams carbon is present, and 71.65 grams chlorine is present. Step 2. Conversion into number moles of each element. Divide the masses obtained above by respective atomic masses of various elements. Moles of hydrogen equals 4.07 grams by 1.008 grams equals 4.04. Moles of carbon equals 24.27 grams by 12.01 grams equals 2.021. Moles of chlorine equals 71.65 grams by 35.453 grams equals 2.021. Step 3. Division of the mole value obtained above by the smallest number. Since 2.021 is the smallest value, division by it gives a ratio of 2:1:1 for H is to C is to Cl. In case the ratios are not whole numbers, then they may be converted into whole number by multiplying by the suitable coefficient. H is to C is to Cl equals 2:1:1. Step 4. Writing empirical formula by mentioning the numbers after writing the symbols of respective elements. CH2Cl is thus the empirical formula of the above compound. Step 5. Writing molecular formula. Determine empirical formula mass. Add the atomic masses of various atoms present in the empirical formula. For CH2Cl, empirical formula mass is 12.01 plus 2 into 1.008 plus 35.453 equals 49.48 grams. Divide molar mass by empirical formula mass. Molar mass by empirical formula mass equals 98.96 grams by 49.48 grams equals 2 equals N. Multiply empirical formula by N obtained above to get the molecular formula. Empirical formula equals CH2Cl, N equals 2.